So let's see, we've got, oh, and right off the bat, fix the lighting. So we got, everybody with me? 3 different boxes. And clearly they're all from a diversity of different shipping companies. There's a theme here. Anybody know what the theme is? Not just rivers, the biggest rivers. Right? Because the biggest rivers deliver. Everybody knows that. All right. So we've got this first box from the Yangtze Shipping Company. And of course we're going to have an FG acting on it. If you recognize anybody recognize the landscape that we're on here? This is like some high-level graphic design. Spent some solid time in, not even Photoshop, it was like Google Shapes, I think. Anyway, FG, what else is going to be acting on this box if it's just sitting there? Starts with an N. Yeah? Normal force, yeah. Normal force. Now, if it's just sitting there, we're all good. If I did this, can you believe that I could apply a force, but it's sitting on real ground, like real Minecraft ground anyway. If it was moving at constant velocity to the right, couldn't I also have an FK? FK go this way. I can make my FK be the same size as the F applied. If it's the same size as the F applied and I'm claiming that it's moving, then it must be moving at a constant velocity, right? And so this could be just like a box sliding along. And you know, if I'm stuck in video game mode, maybe it's sliding along and some plumber is jumping over it or something like that. But anyway, I'm mixing my platforms, I guess. Let's take a look at this one. This is one where we talked about this a little bit yesterday. If it was a box with the same mass, this Nile box, the FG would be the same. However, if I were to take an applied force and apply it, and we're just thinking qualitatively here, I have my applied force. I'll label it down here because it's outside of the graphic. F applied. How could I decompose this force? Break it down into X and Y. Yeah, so F applied X and F applied Y. So we could have FAPX, FAPI, and as soon as we have a FAPX and a FAPI, what would happen to the normal force? Like, assuming that it's not accelerating up or down, what would the normal force do in this case? Just qualitatively help me out. Yeah? Yeah, it'd be bigger than FG. Thanks, Will. All right, so we're going to make it be, I'll over-exaggerate it, bigger than FG. And we know that mathematically the FG and the F applied Y would add to the F normal to sum to 0 if this thing isn't accelerating upwards or downwards. But then, like, at the same time, what would happen to the FK? Alex? An increase, yeah. So again, I'm over-exaggerating things a little bit. Now, if I get to the point where this FK is greater than the F applied X, is this thing going to move? No, probably not. It won't. In fact, it definitely won't, because static friction force is even bigger than kinetic friction force. So if I ever get to the point where the FK, because the normal is greater than the F applied X, this thing isn't going anywhere. So that's a nice thing to keep in mind. Now, mathematically, I would have figured that one out already, because I probably would have called to the right positive, and I would be getting a net force in the X direction that's negative, and there's no way that friction force can drive the system. But we're kind of going through the patterns of thinking. But that would be like my final stage of thought. If FK exceeded F applied X, this thing is not moving. Okay? Let me look at the Mackenzie. Anybody know where this is the biggest river? Really? It's not Scotland. Yeah.
Is it in America?
It's in Canada. It's in Canada. All right. No points for geography. All right. So, yeah, if I use the Mississippi, you'd be like, all right. Anyway. If we had an applied force that was going like this, if it had the same mass as the Nile and the Yangtze, we got the FG. You guys tell me, what would my thought process be? What would I have to think out next?
X and Y components.
X and Y components, yeah. Thanks, James. So I got my FAPX, I have my FAPI. What's the next thing that I would probably want to think out? Alex? Yeah, what's it done to my normal force? Yeah, it's reduced it. So again, I think I'm kind of stuck inside the graphic there, but hopefully you can see that there's an upward arrow and it's smaller than the force due to gravity, kind of stuck behind the tape on the box. And then compared to the previous two, what would this do to our FK value? Decrease, yeah. And so hopefully like we were able to think through all this stuff quite easily. Hopefully that was all smooth from the homework. This is just making sure that everybody knows why the solutions that you looked at were what they were. Because I know I had a few people that were coming around either at lunch or after school yesterday to ask some questions. Now today we're going to change things a little bit. We're going to turn the world on an angle. And it's not even complicated because I know like my own kids did this in elementary school. They did like inclined planes and levers and all that sort of stuff. And we're not even doing levers right now. That would be a torque issue. Not that it's beyond you folks, it's just not what we're doing. We've got this object on an angled surface, an inclined plane, and we're still keeping our same graphics. That high-end stuff, right? We can have ourselves an FG. And actually, you know what? I want to do a little bit better just because I want to be able to see this outside of the image. I think I'm going to take my FG a little bit lower. I have an FG that goes like this. Now when it comes to normal force, because that was one of the things that we were going to before, the normal force is by definition perpendicular to the system, or perpendicular to the surface on which an object presses. So I've got an object sitting on a surface, and that object sitting on a surface has a normal force. The normal force is perpendicular to the contact surface. So I'm going to claim that this guy here is my normal force. Notice I don't have anybody pushing on this one. There's nobody pushing on an angle, nobody pushing straight, none of that sort of stuff. I'm just keeping it simple for now. I want to think about what would happen if this box slid down the hill. That seems like a reasonable thing. What direction would the friction force point in? What do you say?
Like back up?
Yeah, you're right. Yeah, back up the hill. Makes sense. It's going to go that way, parallel to the surface upon which it's sliding. So we could say we got an FK going that way. Now I kind of think to myself, like, all these forces are at weird different angles to each other. Nothing's perpendicular to each other. Nothing's parallel. Can I fix this situation? And like the answer is yes. I can fix this situation. I'm going to have to deal with it in components. But it's a set of components that we haven't had to deal with before. So I'm going to bring out some colors to make sure that we can see what we're doing here. What I want to propose is that I could take force due to gravity and break it into components. But the components I want to break it into are different kinds of components than we've had before. I want to say that I'd like to, since the world has been rotated, I'd like to rotate my reference frame. And instead of having up, down, left, right, I'd like to say that there's a perpendicular direction and a negative perpendicular direction, perpendicular to the surface of contact. I'm going to say that there's a parallel direction and a negative parallel direction. So that's the, if you like, it's the perpendicular symbol, upside down capital T, some people might think of it as, and the parallel symbol, the two lines next to each other. Okay? I say, okay, well, hold on. If I'm going to think about this reference frame, normal and kinetic friction are already in line with that reference frame. So this FG is going to have a component that I would call FG's parallel component. Perpendicular component. FG perpendicular. And there would be a component of FG that would be parallel to the sliding surface. You've got to be able to find a way to calculate these things. And so there must be some angle. Whatever this angle is right here. First I got to do a quick little angle proof. It's not much of a proof. It involves Z patterns and F patterns. So I just want to make sure that everybody can see it. Because once we've got the proof down, we'll just make use of it. But I want to be able to have evidence for what I'm about to claim. So I want to draw a picture. This is a quick vector diagram just to help us out with the thought process here. I'd like to say that my ramp is this ramp that's at an angle. And I'm only just drawing this again so that I can make a mess of it without making a mess of my primary illustration. There's my mass. Here's my force due to gravity. And then I want to do an offset line. And I'll do the offset line in red. But my offset line is parallel to my angle of incline. And then I want to draw another construction line, and it's going to be perpendicular to that offset line, so it's going to go like this. Straight through the center of mass of the box. And then I want to do another parallel line that's in line with what I formerly called the parallel component of force due to gravity. And then I want to think about the fact that the FG vector creates a right angled triangle with the ramp. Now I could, just for a second, off to the side, I could call this guy here angle phi. And I could define for myself that 90 minus theta equals phi. Now the reason I could say that is because there's 180 degrees in a triangle, and so theta plus phi must be equal to 100, or must be equal to 90, right? So theta plus phi must be equal to 90. Fair enough. So I say, okay, well hold on. If this guy here is phi, this guy here is theta, it seems to me that there could be an angle here that would also be theta by similar triangles, which means that this guy up here by similar triangles also has to be equal to what? Starts with an F. Not really, starts with a PH. Phi. It's phi. Okay? So that angle up at the top has got to be phi. And then I realize, well, wait a minute. Those two dotted lines are at right angles to each other, are they not? Because one's perpendicular and one's parallel, which means that this angle right here, doesn't that guy have to be theta? Now that's, I think, just about the quickest little proof I can do with that. It's a lot of angles, but it only involves a few characters, right? And all that is to say that the angle of incline of my ramp is the same angle as the angle between FG and FG perpendicular. Okay? So a little bit of scribbling here. Hopefully all that, supplementary, complementary angle stuff makes sense to you. Little F pattern, Z pattern, that sort of thing. Hopefully it feels good. Now, there probably are like 3 other ways to show the exact same thing. That's like very quick. Everybody feel satisfied with it? Right? So I just need evidence that that's the same angle. And if I were to play cut and paste, I bet you I could flip this triangle here around and rotate it and show that it's similar to this triangle here. We could probably believe in that, but I just needed to have evidence, okay? Anyway, the reason that we do that is so that we can do this little aside. We can say, okay, well then FG perpendicular has to be equal to, because look, hey, FG perpendicular is the adjacent, because these two vectors are at right angles to each other by definition, perpendicular and parallel. FG perpendicular has got to be FG times cos theta, and FG parallel has got to be FG times sine theta. And this is kind of that default intro thinking that we would think about if we were doing like a projectile problem. You always just find out what F1x is and what V1x is and V1y is for an angled projectile. We would do the same kind of thinking with an object on an incline. We would by default find the perpendicular and parallel components for the force due to gravity. That would be an automatic thing that we would have in mind. Now, if this situation also has kinetic friction, it seems to me that the force due to gravity perpendicular is going to contribute to that normal force, right? So somehow that kinetic friction force is also going to be involved. So I want to think about what the systems of equations could be for this. So I could say, well, in the perpendicular direction, we could say F net perpendicular is equal to the F normal. And you know, we could say plus FG perpendicular, but I think I'm going to say FG perpendicular is in the negative direction, pressing into the incline, so I'm going to call it negative FG perpendicular, only just because it's pulling us in that negative perpendicular direction. But then I've seen things on ramps, and I know that they don't crash through the ramp, and I know that they don't blast off the ramp. So what's F normal in the perpendicular direction? 0. Yeah, and we kind of seen this up above with the simple Yankee problem, right? F net in the y direction is 0. Same with those simple boxes at the top of the page. I mean, that was how we came up with those normal forces. That was the same kind of assumption, the same thinking pattern. So on an angle, same idea, it's just that we're on an angle now. And then we would say, okay, well in this case, provided that there's nothing like pushing up on an angle or pulling down on an angle, because you better believe that would make it more like a Nile or a Mackenzie problem. As long as there's none of that business going on, I could just say that the F normal would be equal to the magnitude of FG perpendicular. Because I'm just going to get that normal all by itself. And I could also say that FG perpendicular, like I said to the left-hand side over here, FG perpendicular is equal to FG times cosine theta. And if I wanted to expand that out further, it would be mass times acceleration of gravity times cosine theta. And if I wanted to plug in my values, I could do that. Oh, did we give a mass to this? Oh yeah, it looks like there's some information here. It says that the mass of this box is 10 kilograms, and it's on an incline at 30 degrees, and there's a coefficient of friction of 0.05. So I've got a mass of 10 kilograms, 9.81 meters per second squared, cos 30 degrees. And somebody with a calculator, what's the F normal on this box? Anybody got it? Starts with an 8.
84.95709.
95709? Nice. All right. And it seems like if I was going to think this thing out, I mean, the question itself says find the acceleration. If I was going to think this thing out, I've got an F normal. What's the next thing that I should do? Yeah. Love it, yeah. So I could say, all right, well, Fk is going to equal UKF normal. UK is 0.05. F normal, 84.95709, according to EV. And I get an answer that starts with 4. What do you guys get? I'm just checking my own math here. I want to make sure we all get the same answer. Anybody? Audrey? 785 newtons. And because of the reference frame, I'm going to force in a negative sign here. Okay? Just to remind myself. Now, if I want to find the acceleration of the system, again, what's the next step? Lead me through this thing. Alex?
Parallel and apply force.
Okay. And we got to think about friction too.
Just add F parallel.
All right. So we can call this F net parallel. Pardon me. Cough. FG parallel plus FK. Now I've written it as positive FK because in my thinking today, I'm going to sub in my negative value. If you had calculated this as a positive value and you wanted to leave this as minus FK, totally valid. You just can't do both. You got to do one or the other. So that's FG times sine theta plus really UKF normal, but we've already calculated it. And when we sub in our values, we've got 10 kilograms times 9.81 meters per second squared times sine 30 minus 4.24785. That's my unrounded value. What's the F net? Again, it starts with a 4, I believe. Anybody got it? I feel like Peyton's got it. 80 what? 3? Okay. All right, and that's newtons. And then if we're going to find the acceleration, we're just in Newton second, or yeah, it's Newton second law mode now. So we could say acceleration is equal to, we can call it the acceleration of the system, but it's just one body. F net parallel over the mass of the system. 44.803 newtons divided by 10 kilograms. And we end up getting that 4.4803 newtons. And I think we only had 3 sig figs to start with here, so 4.48 newtons. And the right way to say this direction, right, it's meters per second squared. You got me. Thanks, Will and Will. Meters per second squared. And the right way to do this direction, this seems kind of convoluted because some people are going to say, oh, couldn't we just say the positive parallel direction? Really, it's 30 degrees below horizontal. That's the true direction of this thing. I mean, think about it. If I'm going down a ramp, again, this maybe is some Z pattern thinking. If the ramp has an angle of 30 degrees and it's traveling down the ramp, then by Z pattern, it's going 30 degrees below horizontal as it travels down. Okay, so that's the proper way to express that direction. But yeah, I understand what people say when they say positive parallel direction as well. Now, there's always people that say, well, all of that, could we have written a generalized equation? And of course the answer is yes, right? Like, I mean, I can do a little bit of backwards thinking and I can say, okay, well, the acceleration of the system, that's going to be F net parallel. Well, F net parallel was Fg parallel plus Fk divided by the mass of the system. Could I expand that out? Yeah, Fg parallel was Fg times sine theta plus Fk would have been expanded out to be mu k. Now I could say times F normal, but remember F normal was equal to Fg perpendicular, or at least the magnitude of Fg perpendicular. So Fg times cosine of theta. And all of that divided by the mass. And even then we could expand it out a little bit more. We could make those Fg's have mass times acceleration due to gravity embedded in them. Or I could factor them out altogether, and we could write it out as equals mass times acceleration due to gravity times sine theta plus mu k cos theta, close bracket, all of that divided by mass. And then you think to yourself, well, wait a minute, isn't there a mass in the numerator and a mass in the denominator? Well, yeah, and the masses would cancel out. And then you realize, well, oh, this is a mass-independent problem. And I didn't even need to know the mass in the first place. And that's actually another nice thing about generalized equations, is that sometimes you realize that some of the variables are useless. And it makes the world just like a little bit simpler, you know? So, nice to have all that kind of math skill under our belts. But again, this is something I want you to play around with. It's generalized equations, not something that's being tested on.